Hi everyone, welcome to Math's Spellbook. I'm your host Peter, and basically we are going to engage in a little bit of, I guess, a Calc 2 review. If those of you who have already taken Calc 2, you know this might be a review for you guys, and if not, basically this is about infinite series tests. Now, since I've taken Calc 2 before, I am familiar with sequences, although the thing of it is that, does that mean I remember how to solve sequences problems? No. No, but I just wanted to review, I don't know if it's going to be quick or if it's going to be like pretty time consuming, the series test, like all the series tests up from, what's the first one? The geometric series test all the way up to, I would have to say, all the way up to like the alternate series test. Like, I don't remember what the last test is, that because like every textbook's different, and I think every textbook goes over like all the tests, and I think the last one is the alternative series test, because I think that's after you learn the root test and the ratio test, which are, both of them are my favorite tests. Actually, I love the ratio and the root test. Of course, like, you guys didn't ask, but I felt like I should just tell that anyway. Hey, Sidebuzz. Yeah, thanks for the lurk. Thanks for the lurk. I appreciate it. Anyway, let us get started, shall we? So I'll turn on the study timer, and I think we can just, I think we'll just go over here. Yeah, because I think they list all the tests here in this chapter. This is review. Oh, here we go. So I think we're going to have to move the chat. I'm not sure where we'll move it. Actually, we'll expand our book view, and then we'll just zoom in a bit. We'll zoom, we'll go over there. Hopefully you guys can see that. Because I haven't done any of these tests like in a long time, so I figured like now is the perfect time to actually start reviewing, because the reason why I want to go over this test is because I know when you get into differential equations, like, there is a point where you actually need an infinite series. So I figured I would just go over these. Alright. So we have the geometric series test. Excuse me, sorry. I just took a drink of water. Okay, so if it's less than 1, and then we have the divergence test. So I'm happy that they actually put all the tests here so you can actually see them all. It's a really great list. I think I was writing these down. I remember the P-series test. This one was pretty easy to, like, I think some of them are pretty easy to remember because the divergence test, this one is just basically you just look at it and see if it diverges. And if you're not sure, you can just do the limit test. I mean, well, it's not a limit. It's not. I call it the limit test, but you can test it by just basically putting the limit to infinity. If it's not too obvious. So the geometric series test. And P ratio. These two are my favorite, the ratio and the root test, because I think like, you implement a technique to like basically see what happens. The only thing is that if it equals the 1, I just have to remember if it's the same for both. So I think it converges when it's less than 1. Okay, so it has to be less than 1. And if it's greater than 1, then basically it diverges. I wonder how the math proof was for the ratio test and the root test. It must have been very hard for the mathematician to actually prove that. Okay, the comparison test where it's greater than 0. So A is greater than 0. Oh wait, 0 is... What? Oh, 0 is less than. Okay, I was like, am I reading that backwards? 0 is less than AK, and then basically, and A is less than or equal to BK, and BK converges. Okay, so basically you just compare this to another series. So we might have to practice the comparison test. So it diverges when, so BK is greater than 0, but then it's less than or equal to A, and B diverges. Yeah, this is the one I think I get confused with sometimes, because I think there's a certain, because like the way they phrase it is kind of strange. Let's see. I want to make sure that my mic is okay. My mic is hooked up. Hopefully you guys can hear me okay. Okay, so I think we can go back a few chapters, because I think we have to do some review on the comparison test. Okay, limit comparison test. So this one. Okay, here we go. Root and comparison test. Oh, okay, so it's all in the same chapters. Well, actually, let's look at an example, because I know when you do series, you have to show that you have to prove it. So, okay, because I actually did some, I think, root test problems last night, and I wasn't sure if I was writing the last part right. So when it's okay. Okay, the comparison test. Here we go. Comparison test. If let sigma A K and sigma A BK be series with positive terms. If 0, okay, we read that. And A converges. So B has to converge. And if B... So I'm guessing for this one, you actually have to look at the series and see which one is like, I mean, when you're comparing it, like if it looks like a certain series, I think. So let's look at what, oh, they have a proof of it here. B. Interesting. Okay, do they have any examples? Okay, here we go. Use the comparison test to determine whether the following series converges. So case 4. So -1. So then you can basically compare that to, because I sort of remember how to do this. So basically it's like, now you basically compare that to say like 1 over 4k, 1 over the k to the 4th power, I believe, because that is particularly greater than this one. No, wait, it's like -1. Oh, so we would have to put like 4k. Right, yeah, here we go, yeah. So roughly these converge. And then that reduces. Yeah, because I remember the tricky one is when you have +1. When you have +1, then you're going to have to do something a little different. You're going to have to do something a little different, because that's when it gets a little tricky. I remember that part, and that part like would always like kind of like I don't even know if I got tricked on that part. I think I did. Knowing me, I probably would have gotten tricked when it comes to those type of problems. Explain why the series 1k as a comparison test to 1k plus 1. Well, let's see. the thing of it is that this would diverge. And if this diverges, then this one will diverge. Because, like, because of the p-test. It fails for the p-test. So, given... Well, so this is like one of those, comprehension questions. Like, you have to actually comprehend what's going on. So, basically, like, because this one fails the p-test, this would also fail the p-test. Because it's k to the first power. Even though it's +1 underneath. I mean, this is less than this. But still. Yeah, those are the things that I think screws up a lot of students, including me. Where you think that this one would be less, but then when you look at this, it's actually... This one is less than this. And I think that's usually comes from, like, algebra. Like... But sometimes people forget because it's like, oh, there's a bigger number down here. But they forget that the bigger this number is on the bottom, the denominator, it means it's closer to 0. So it's one of those tricks that you kind of had to go back to when you're like learning this stuff. Okay, the limit comparison test. Okay, so what is this one? Okay, the limit comparison test. Let sigma AK and sigma BK be a series with positive terms. Let's limit... Oh, okay, so you put them on top. So you put A in the denominator and B in the... I mean, you put A in the numerator and B in the denominator. Equals a limit. Okay, so... Let's see. 0 is less than L, and L is less than infinity. L is a finite positive number, okay. Either both converge or diverge. If L is equal to 0 and B converges, then A converges. Okay. If L is equal to infinity and B diverges, then A diverges. Okay, so these small details are the things that I think I would miss, because I would have to remember that if it equals 0 and B converges, like I think I would forget the B converges part. And I think most students would also make that same mistake. If I make the mistake, then I'm pretty sure that some students will make the same mistake I would. So, oh, they actually show you the proof of it. Oh, they do it through the epsilon proof method, which I still have to like actually learn, because I'm not really great when it comes to epsilon and delta proofs. Okay, use the limit comparison test to determine whether the following. So I'm guessing... So I'm guessing this would be A and this would be B, and then if you put the limit... Actually, let's try it. Let's try it before we actually start answering stuff. Alright, so we have... dot... So we have sigma to infinity, k is equal to 1, k4. So we'll have to use the limit comparison test for this one. Okay. So... I mean, technically, if you set it to infinity, this will... If this part is B, then that means it's going to diverge. That means A is going to diverge. Yeah, it looks like the... K to infinity. Yeah, because if this is A, this part... This part. So they will go to infinity, both of them. But let's see if we can do L'Hopital's rule. So if you take the derivative, then you take the derivative again. I think it will still remain the same, because then you're going to have to keep doing it over and over. Unless you can reduce it all the way. 5. That's 1. But I think you can still do it again. Oh, hold on. This is 4. I don't know why I froze right there. So then we get 24k. And then this would be 3. And then we can just reduce this to 0. Oh, what a coincidence. We can actually reduce it even more. So we can just reduce it to 1 for 10. And then we had 2k. So that means it's going to go to 0. So if the limit equals 0 and B converges, then A converges. But when you look at it normally, I mean, if we didn't do L'Hopital's rule, then I mean, technically it would go to infinity. How to think about this one? Because B kind of diverges, but then the limit turns out to be 0 if we do L'Hopital's rule. Huh. Did I do that wrong? Let's see. Oh no. Oh, okay. Oh, that's where my thinking was wrong. Okay, so you have to think of it like the p-test. So it's like a p-test inside. Oh, okay. That's where I kind of made a flaw in my logic there. Oh, okay. Okay, yeah, I was way off. I thought, like, basically you have to think of this as like A and B, but so that we can pair these. Then you flip that over, and then you cross those terms out. And that leads to infinity. Let's see, case 3 does not apply here because the comparison with the series converges, so the test is inconclusive. If instead we use the comparisons, then... Oh, okay, so you can get an inconclusive with these tests. A bit more cunning. Becomes conclusive. A series between... Oh. That's a pretty interesting one. let's see, this limit by recalling. It grows slowly. Oh yeah, I probably have to remember the rates of which these grow. I always forget those. I always forget the rates at which they grow. I think they have a list here. Where are the growth rates? Where are the growth rates? Maybe it's in the... Let's see. Converge. These are infinite series. Okay. Alright, where are the rates of growth? Oh, here we go. The growth rate of sequences. Okay. The following sequences are ordered according to the increasing growth rate as n to infinity. That is, if an appears before a bn in the list, then the limit from n to infinity a over b equals 0. Limit infinity b over a equals infinity. Okay, I think I probably should write this down because I always forget this. So according to them, it's q is less than np way less np which is less than n, which is less than n to the n. Okay. So growth rate of sequences. Yeah, I always forget this one. So what's a good way to remember this? So n to some power p equals so I think the way to remember it is if there's a natural log, it's going to be slower than a number to itself power. And I'm guessing the n is supposed to represent when n goes to infinity. So if b goes to infinity, then that means that's going to be bigger than n to some number. So the natural log of our, I guess, like our variable in this case, which is n. Okay, so I think that alright, so let's see if we can do some problems then. Evaluate the geometric series or state that it diverges. So in this case k, if it's less than 1, then it converges. If it's so in this case, So we got 19. So this is geometric series. So in this case, it will end up being 1k over 4k. So 1 is just going to be 1 when it goes to infinity. But then like 4k is going to be going to infinity, which means it's getting closer to 0. So in this case, if we take the limit when k goes to infinity, yeah, that didn't look right. I'll rewrite that, make it look nicer. So we'll just call this f of k. We'll call it f of k. So f of k converges hold on. I think I'm mixing up my tests. Because geometric series is supposed to be less than, unless I'm not doing it right. Let's take a look here. Oh yeah, so basically r is not k, r is this, so it's less than 1. So basically it passes because it's less than 1. Okay, so what does it say when it's like greater than 1 for this test? So I guess you classify it as that it diverges when it's greater, when it's like 1 or greater. So technically 5, so that'd be 0.6. Yeah, 0.6, and then so that's less than 1. So this will converge. And I think there was a formula. There was a formula that you can use for geometric series. So in this case, a would be 1. So you have 1 over minus case would be 4 over 4. Meaning that it would turn out to be 4 over 3. Let's see here. So that's where it diverges to. Okay, so R in this case, which is R is less than 1, and A is 1. So therefore, which is less than 1. 1. Therefore, meaning that it's 10. Well, that is quite mind-blowing. Let's see, geometric series with alternating signs. Ooh, let's actually try this one. So do they talk about any of those? Oh, the telescope series. I forgot about this one. What is the telescope series again? That's the telescope series. With the geometric series, we carry out the entire evaluation process by finding a formula for the sequence of partial sums and evaluating the limit of the sequence. Not many infinite series can be subjected to this sort of analysis. With another class of series called telescoping series. It can be done. Here's an example. Oh, sorry guys, I didn't realize I was reading this portion. Hopefully, like you not able to read it doesn't deter you from what I was saying. So, telescoping series. Let's see. Evaluate the following series. So basically all these like kind of eliminate each other, turning them into 0 if you group them in the right way. Then you simplify, and this will be 0 and be 1/3. Observe the interior term. Oh, sorry about that, guys. I didn't realize our connection got cut, but we're still in the red, so yeah, my internet's not the best, and I think it's about that time of the season where like the connection is going to be like jumping in and out. Okay, we're in the yellow right now, so... And we're back in the green, nice. Yeah, sorry about that, guys. This part, this will definitely go to 0, and then it'll be equal to 1. Okay. They don't cover that much about alternative series, so let's take a look. So evaluate the geometric series or state this. So does that mean you have to solve this similarly to the way you would solve a regular geometric series? So let's take a look here. So 35 series is to 0. Okay, so this is definitely less than, so R is equal to negative, oh whoops, why did I put 5? It's 9, 10, 9 over 10. And R is definitely less than 1. So meaning, and I'm guessing it's supposed to be plus. Over 19, huh? Is that the correct way to actually interpret that result? This one's 9.3, right? Yeah, 9.3. Chapter 6. Where are you? Chapter 9. Chapter 8. Chapter 9. There we go. Here we go. Number 35. Yep, that is right. Okay, so it's the same method. It's the same method. Okay. Back over here. We'll zoom in. Yeah, we're on this section right here, guys. Okay, so we'll do another one. Let's see. Which one should we do? Let's do the one with the E in it. K is negative in this case. Then that means the way it looks. That would be close to 0. And this is an even number, so I'm going to check out Quizlet, because I feel like that was kind of I don't want to say that was easy or anything. Calculus for Einstein engineers, infinite series, number 38. I feel like that might not be right. Let's take a look. Alright, here that can be rewritten as okay. So technically it's supposed to be this. I mean, that is still technically correct. We just have the wrong sign. So it's this. Yeah, that one is a pretty tricky one, because you have to remember that like negative K means that like the E goes on the bottom. Now, all right, break time. Okay, it's kind of good to get like a little bit of review on the basic stuff. Oh, there's a new Veritasium video out. Maybe we should take a watch. Let me just pause my music here.
Imagine.
Let me just drag this in here. Expand it a bit. Take a watch for this until our next study session.
You are an astronaut out drifting in deep space. When you throw a rock as hard as you can, what's going to happen to that rock? Well, you would think that it would continue with constant velocity in a straight line. That's just Newton's first law. But what actually happens is it eventually slows down and stops. So why does this happen? Where did all the rock's energy go? At the turn of the 20th century, the problem of energy conservation baffled some of the greatest minds, including Albert Einstein. Einstein came up with a possible solution. But then, a little-known unpaid mathematician named Emmy Noether proved he was wrong. And in doing so, she created a whole new paradigm for physics, one that underlies all of particle
Noether's
physics
theorem.
and explains why anything is conserved. It all started in 1915 at the University of Göttingen, where Einstein was giving 6 lectures on his new theory of gravity, what would become the general theory of relativity. The lectures were well received, but Einstein hadn't yet settled on the final form of the field equations. One problem he was facing was how to show that total energy was conserved in his new theory.
This is the whole beginning of this story, right? Classically, they thought they had this understanding of what the energy of a gravitational field was. All of a sudden, with these new equations, they go, where is it? Is it in the curvature? Is it in the stress energy tensor? Where's the term that we're looking for?
Einstein suggested that the principle of conservation of energy, long established as a bedrock of physics, might hold the key to working out the correct field equations. In the audience, legendary mathematician David Hilbert was intrigued. So he started to look for the energy conservation equations in Einstein's new theory. But the best he could find was a set of equations known as the Bianchi identities. They showed that energy was conserved, but only in a completely empty universe. So for one like ours, filled with stuff, they seemed useless. Hilbert was stumped.
Fortunately, he knew just the person for the job. His new assistant, Emmy Noether.
From an early age, Noether had dreamed of following in the footsteps of her father, a mathematics professor at the University of Erlangen. She got special permission to attend lectures at the university, but they refused to admit her as an official student. The Erlangen Academic Senate held that the admission of women would overthrow all academic order. So, in 1903, she spent a semester.
Yeah, it kind of sucks that, basically, back then, women, weren't able to get, a higher education, even though they were, incredibly brilliant. And, now that, even though we've came so far, there's still a lot of work to be done. And, women, as well as minorities, still have to, I guess, show that they're willing to go the extra mile to, prove their place in society. So it's something that I think anyone would feel as if they're not doing enough. And the thing of it is now we have all these great figures that have or trailblazers that set the way for all of us to actually progress forward, so all of us can be educated and all of us can do brilliant things. But we still have a lot of work to do when it comes to as an acceptance and basically showing that people are capable of more than what we think that they're capable of.
At Göttingen instead. There she learned about a new way to approach geometry, using symmetry. Symmetry is one of those ideas that's easy to recognize, but harder to describe.
If I align a mirror on this triangle like so, then it looks the same as without the mirror. And that's because this is an axis of symmetry. Reflections about this axis leave the triangle unchanged. And the same thing happens if I put the mirror like this, or if I orient the mirror like this. So this triangle has 3 axes of symmetry. Now, mathematicians generalize the idea of symmetry further to be any action you can take that leaves an object unchanged. So something else I could do is I could rotate this triangle by 120 degrees, or by 240 degrees, or by 360 degrees. Together, these 6 actions capture all the symmetries of the equilateral triangle.
But you can also have more abstract symmetries. For example, with a mathematical function. If I shift this function up or down by some constant amount, call it a, then all of its y values will change. But if I differentiate that function, I get the slope, and that remains unchanged regardless of whatever constant is added. So you can add any constant to this function, and its derivative always stays the same. So there's a kind of translation symmetry. And unlike the symmetries of the triangle, this is a continuous symmetry, meaning you can shift it by any amount you like. Over the next 12 years, Noether became a leading expert on symmetry. She became only the 2nd woman in Germany to earn a PhD in mathematics. And she used this expertise to help Hilbert and Einstein with their problem of energy conservation. The issue had bothered Einstein so much that he proposed a new conservation equation. It said that if we add together the energy of matter and the energy of the gravitational field, then that total remains constant. Its change over time and space is zero. But when Noether saw this, she was convinced Einstein had made a fundamental mistake, because this equation disregards the foundational principle that general relativity is built on.
Oh. Dang.
10 years earlier, in 1905, Einstein had introduced his special theory of relativity, and it was built on the idea that the laws of physics were independent of your frame of reference. But so far, Einstein had only applied this principle to inertial frames of reference. Those are frames that move at a constant speed.
He began wondering what would it take to generalize that, to consider more general states of motion. After all, trains on the platform. He loved trains. Trains would speed up or slow down. People, moving around the world don't only move at a single constant speed forever.
In 1907, he wrote, "Is it conceivable that the principle of relativity also applies to systems that are accelerated relative to each other?" This made him wonder, perhaps his principle could also be applied to accelerating and rotating frames that move in any way in general. That's the general in general relativity. So Einstein got to work on this largely intellectual pursuit.
But then, as he was daydreaming in the patent office, he had what he called the happiest thought of his life.
He imagined the window cleaner at the top of the opposite building falling off. And Einstein realized that while the man was falling, he wouldn't feel his own weight. He would be weightless, and anything he dropped on his way down would remain stationary relative to him. It would be just as if he was floating in outer space.
It's ironic. We would have said, he's being pulled down to the ground because the gravity of the Earth is exerting a force. But Einstein said, while that person is in motion, what we call free fall motion, they would actually feel no gravity at all. So there must be some equivalence between accelerated motion and the action of gravity. So Einstein arrived at what he called the equivalence principle.
If you were stuck in a rocket in outer space, accelerating at 9.8 meters per second squared, then it would be the exact same as if you were standing on the surface of Earth.
And this was huge, because it meant that if Einstein could figure out how to understand accelerating frames, then he didn't just get a more general theory, he would also have a new theory of gravity.
But to achieve this, Einstein needed to make sure the laws of gravity had the same form in every frame of reference. This is the idea of general covariance, and it's one of the core tenets of general relativity. To satisfy it, Einstein knew he had to use special mathematical objects called tensors. A simple kind of tensor is a vector. You can write a vector as a set of components
That's what I need to
multiplied
learn.
by their basis vectors.
Tensors.
For example, this vector can be written as 3x hat plus 2y hat. But I can also write this using a different coordinate system. And with these new basis vectors, the original vector is now written as 2a plus 1b. So the components, the numbers in this list, changed, but the vector didn't. It stayed the same. And that's because when the basis vectors change, the components adjust in a complementary way to keep the vector the same. The vector itself is independent of which coordinate system you use. And the same is true for tensors, only now instead of having just two components, a general tensor can have any number of them in the form of a matrix. And just like with vectors, you can change a tensor from one coordinate system to another, and the tensor stays the same. So that's why Einstein had to use them to build his new theory.
And that was exactly the problem that Noether found, because when she looked at Einstein's proposed energy conservation equation, it contained a pseudotensor. And as the name implies, that isn't quite a tensor. When you try to transform it from one frame of reference to another, it doesn't remain the same quantity in different frames. The gravitational energy you might observe in one frame completely disappears in another.
And Einstein, he had some strange thoughts about this. I mean, people were trying to
maybe those of you who are more
conservation
mathematically
energy
literate
into
can
relativity
enlighten
by
us about that.
bending the rules of mathematics.
So Noether knew that Einstein's proposed solution couldn't be the answer, and that made her think. What if general covariance and energy conservation are simply incompatible? And if that's the case, then why? General covariance says that laws of physics must stay the same when you change reference frames. So that is a kind of symmetry, exactly what Nutter had spent her career studying. So she started thinking about the symmetries of the universe, beginning with the simplest possible case, an empty, static universe.
Imagine you're an astronaut in this universe. Since it's empty, there is nothing special about any particular point. I mean, it doesn't matter if you're over here or over there. The universe is completely symmetric under translations in space. So suppose you throw a ball. Well, it'll travel at a given speed, and after a short amount of time, it will have traveled some distance. But since the laws of physics are the same here as just before, we can shift the whole universe, and we're back to the situation we started with. And we can keep doing this over and over, and this shows us that the object will continue with that same speed indefinitely. So what we've discovered is that the principle of conservation of momentum is a direct result of the fact that there's a translation symmetry in the universe, that an experiment done in one spot will give identical results to that same experiment done somewhere else. You could move everything from one place to another and the physics won't change. Similarly, the laws of physics don't depend on whether you perform an experiment like this or rotate everything by 90 degrees. This universe is symmetric under rotations. So imagine we take a metal rod and spin it. If we let it rotate for a minute, then it will have moved through a small angle. But we can rotate the whole universe back by that same angle, and now we're at the starting position again. And we can keep doing this so that each instant looks exactly the same as the one before, which means the object will keep rotating this way indefinitely. So the law of conservation of angular momentum comes from the rotational symmetry of the universe.
Now, another important symmetry of this universe is time symmetry. The laws of physics don't change over time. If you do an experiment today or tomorrow, you will get the same result. So what does this symmetry lead to? Well, to understand this, we're going to dig into some math and a different way of doing mechanics using the principle of least action.
Previously on
Didn't mean to do that,
Veritasium,
guys,
we
sorry.
learned that everything always follows the path that minimizes a quantity known as the action. This is equivalent to the integral of the Lagrangian L over time. In the simplest case, that's just the kinetic minus potential energy. Euler and Lagrange found that the principle of least action is obeyed so long as this set of differential equations is satisfied.
So Noether used action to see how physics was affected by different symmetries.
So suppose we do an experiment where the result is the same now as some tiny time interval epsilon later. Then how does this affect the action? Well, the time is going to change from just t to t plus epsilon. And as a result, the Lagrangian is also going to.
As much as I want to continue watching this, because it's going to go into much of the nitty gritty of Noether's theorem, I feel as if we should go back to the study session. But that was a pretty fun watch. I will, if you guys are watching this on YouTube, I will definitely put this link in the description. So I just got to remember that when I put this in, paste the link there, and then I'm just going to put the title. So remembering where I got it from. Veritasium. Title: The Woman Who Fixed Einstein's Mistake. Okay. So if you guys want to actually check out more of that video, you can basically click the link in the description down below if you're watching this on YouTube. And I will actually just put this link into the chat for all of those who are watching on Twitch, so you guys can check it out for yourselves. So let's get back to the book. I think I closed out everything by accident. Let me just reopen everything. I forgot I opened all my books in a browser link. Let me just open them back up. So put this here. Turn my music back on here. The reason why I have the linear algebra book is I felt as if just in case if I wanted to go into studying something else, just in case. I want to see if we can do some series exercises in here. Split into fractions. Oh, we probably should practice those. Series questions. I thought they would have them in here. Because there's integrals. I remember my physical copy has like series questions. But all these are like derivatives. Okay, I guess we're gonna have to rely on the book. Okay, so we did practice a little bit with geometrics. Here we go. Series. Okay, there we go. I was like, why is my browser being funky? Okay, divergent test and integral test. Actually, let's practice with roots, with the ratio test. So I will disengage my model, and then we will hit the study timer. So here's the root test. We did I think I did the root test like a little bit last night. The ratio test. I actually love the ratio and the root test. Here we go. Here's some of the ratio test. Okay. Okay, so number 9, ratio test. Okay, so if it's the ratio test, then that means we have to do it like, I think the top one is the one that has the one that highest, and this one. Okay, to infinity. And at this point, we have times k, and then these two cross leads us to 0. So according to the ratio test, if it's less than 1, then that means it converges, I believe. Ratio test. If it's equal to 0 or less than 1, it converges. Okay. So, oops. So this series converges by the ratio test. Let's see. Let's try 14. 14 looks like it's going to be a very interesting one. I pick it at random, so it doesn't seem like I'm trying the same numbers over and over. So this one, it has a higher growth rate than this one. No, this one has a higher growth rate. So when the limit of k goes to infinity, so k plus 1, and that's all over k to the k and k, but then we just have to do some quick knitted reduction. So k plus 1 is k, oops. So it'll be k factorial. And this one we have k so these two cross out, and these two cross out. Leaving us with k over the k times k okay, so in this case, this will go into infinity. They both go to infinity at the same rate. The thing is that the bottom is a little bit bigger than the top. So I'm thinking it will converge to 0 if that's the case. Because technically this would go to infinity, but this one would go to 0. Should we employ Hopital's rule? But that would take us forever if we did that. This is an interesting one. Because we got rid of the factorials. The question is, what does the rest of it tell us, though? Because I feel like they grow at the same rate, but I feel like it's going to go to 0 much faster because this K is... The K on the bottom is higher than this K, like in value-wise. Unless, because the top one, because they both grow at the same rate. So this one will, I feel like the bottom will get to 0 before the top gets to infinity. Let's check out Quizlet. Let's see what the answer is. Oops. I think it's, yeah, ratio test. So this one's number 14. Let's see what... According to this, it basically says it diverges. I'm just trying to look at the reasoning behind, like, the way they accumulated to the answer here. The way they set it up was just kind of bizarre. Because I'll show you I'll show you guys what I see here. So they did the same thing I did. Actually, did I write it right? Yeah, I wrote it like this. Yeah, and then we wrote it like, so we wrote it like this, and then obviously it's just gonna divide, and then this is gonna go on the top, and this one on the bottom. Yeah, they did cross out these, which is what I did. But I'm wondering... is there a K to the K on the bottom here? Huh. Maybe this isn't right. Oh, excuse me, sorry. So this one diverges. I just don't understand why it diverges. Because I'm guessing this is quicker than this. Actually, I want to look up why do we need these tests for differential equations, so we can have like a little bit of oops. Let's see. Non-linear models. Here we go. Series solutions for linear equations. At least they give you a review of power series. I guess my title was a little bit self-explanatory. We're going to get into power series, but we just got there in a different way. Expand this here so you guys can see it. Make it a little bit bigger. The radius and convergence. Yeah, I remember this. This one was actually pretty cool when I first learned it. I mean, learned on my own a little bit. Like, I haven't done problems involving it, but when I was learning it on my own, I thought it was pretty cool. Like, the radius of convergence, or in this case, the interval of convergence if you're doing, like, 2 dimensions. Let's see. The problem states find the power series solution of the differential equation. Okay. Now we're actually getting into example problems. Let's see what this is. Let's see, break the solution into a sequence of steps. First, calculate the derivative of the assumed solution. Okay. Then we have to change the summation indices. I remember the math sorcerer did a lecture on this. Like, he actually posted all of his, I think his differential equations lectures on YouTube. Let's see here. So they both have to be like 0. So in this case, they changed the k. So k is equal to n and k is equal to n minus 1. So in this case, n is k plus 1, which is okay. Then you can put them together, like so. Now because we want... Oh, that looks pretty cool. And we have identified is equal to 0. So then let k take on the successive. K equals 0. K1's the assumed solutions. Wow. That is a pretty long process. Oh, the addition of a power series. Okay, so... Okay, so they teach you like small steps of each one. Very interesting. Very interesting. So this one, you would have to change it. Let's see, right as one power series. Okay, so basically you have to change the indexes. So this one's 2. Let's see, the series starts with the series starts with x for n equals 3. Okay, now we see that both series on the right side start with the same power of x, namely x1. Now to get the same summation index, we inspired by exponents of x, we let k equal n minus 2 in the first series, and at the same time let k equals n plus 1 for the second series. For n is equal to 3, k equals n minus 2, and we can get k equals 1. For n is equal to 0 in k equals n plus 1, we can get k equals 1. So on the right side becomes let's see, find the interval of a convergence. Use the substitution shift summation. So proceed like in example 3. Rewrite the expression level. Okay. So for the interval of convergence, here we go. So find the interval convergence for, so do the ratio test. The series converges absolutely. For less than 1, so times 2. Let's see, power series defines a function. So let's see if we can try this. Okay, so number 1. So I think we're going to be ending up with the alternative series. Oh, actually, I think we can do, I think we can do the ratio test with this one. I think this one will do n to infinity. Then since it's in the absolute value, we can turn this as the limit, which in turn can equal to 1. X's. So X is here. So that means it's just X. So that means it's X. So what's the series start with? 1, right? So that means that's the radius of convergence, or the integral of convergence, I should say. So that one's number 1, right? Yeah, that's number 1. This is number 6.1. So let's see. 4.10. 6.2. So it can equal 1, but let's see, -1 plus. Wait, what's the original series? -1. So if x is -1, yeah, I'm wondering why is it. Oh, it can equal 1. So I guess we just forgot that part. And the radius is 1. So let's see, the radius of convergence, here we go. Let's see. If r is greater than 0, then the power series converges for and diverges for when this is greater than minus. If the series converges for all x, then we write that r is equal to infinity, revolving around the absolute value inequality. The thing I love about like the radius convergence and the interval convergence is like there's like it's like you can go everywhere, but the power series just expands to like infinity at everywhere, but then in certain places it doesn't, which kind of gives you a sense of like, oh, I gotta go to a certain area for like awesome things to happen, which is pretty intriguing. Oh yeah, because there's something in front here, so that's why the radius is 2. But in this case it's 1 because there's only just 1 here, so r is 1 equal to 1. Okay, let's try another one. Okay, let's try number 2. So n times n. So I feel like this one would pass for the p-test. I gotta think about which series test that would be good for this one. Because for the p-test, it would pass and it would converge because, like, p in this case is 2 for like over n. The one thing that I'm wondering about, maybe I should rewrite this, make it easier to see. Shall we do the ratio test again? Plus 1 multiplied by to the second these two cross out. Leaving x times oops. this as n to the second, and then n is here, which would still lead us to, I think, the same result we got last time. N equals, oops, n to infinity. Because these two are the same, so we can just basically like get x again. So the absolute value of x. And what does it start with? It starts with 1, right? So r is still 1. Can it equal to 1? Yes, it can. So it can equal to 1, and then oh, put a little negative sign there. So I think it's the same thing. I'll just check on Quizlet because this one's the odd numbered one. I think I gotta add this book too. First course in differential equations. Textbooks, that one. Add it to my file. And this one's 6.1. So 6.1, exercise number 2. So what was the original function? Oh, it can be negative because it's a square underneath. I was like, what? And the radius is 1. Okay. Okay, let's try 3. Equals 1. So you have to like keep in mind about the original function or the original part of this series. So in this case, we want to do the root test, because it looks like we can do the root test with this one, and it looks like it would be better. Seems like it's getting closer to 0 if we do that. Because did we always do the ratio test for this? Let's see what happens if we do the ratio test. So if we do the ratio test, this will be like this. Nice. To the end like this. Then back and to the, like this. And this one just flips. So these cross out. Technically, these two are the same power, so they can become one. So ends up we get equal. Okay, now and the radius I think is still 1. And then we divide by 2. So the radius of convergence is okay, let's take a look. Six point one. Here we go. 6.1. This one's number 3. So we can't equal a half. We can equal negative a half, but not equal a half. Okay, so I think the next time we probably should take a look more at power series and wondering why the signs change. That's the one thing that I'm wondering. Because I'm wondering when does the sign changes so that we know which, like what we can include at the endpoints. Because I think I'm getting mixed up on how to actually interpret the endpoints. But it looks like with every problem we're doing, we have to do the ratio test. But I think that was pretty much a productive stream because we managed to do some problems involving series. We managed to even get up to power series, so which is what the main priority I wanted to get to. But yeah, so hopefully you guys enjoyed that. Hopefully you got some stuff done while you were watching the stream. And also, again, I apologize for the cutoff earlier. Like I said, my internet is not always the best, so you know, sometimes I will lose connection. So if I do lose connection and you're watching this on YouTube, just skip those parts. And basically just continue on. Or you can just take it as a matter of silence, like me being silent while you're working on the stuff that you're working on. So for my Twitch viewers, I will put in my YouTube channel. If you were able to, if you're lurking, you know, thank you for lurking. If you find my productive streams a good space for you to be productive and like get your stuff done, whether it be working on anything you're doing in school or whether it be just something you're studying on the downside or something you're just working on, like, you know, art or anything, you know, you can just basically like rewatch my streams there if you want to create that that atmosphere of being productive on your own outside of my streams. But also, like, if you want to subscribe to my YouTube channel, you're more than happy to do so. Find out what I'm doing, which math I'm doing, and how my math journey is going. As well as, you can follow us on our Discord server at the Math Spellbook Library Discord. We can basically talk about math, physics, or any type of science, or anything that inspires you. And if you want to tune into my video game channel, my Uncle Talks channel, I will be streaming tonight at 8 o'clock Eastern Standard Time, if you want to check that out. If you guys are watching this on YouTube, all the links will be down in the description below. I also will include a link to Veritasium's video that we were watching during the break time, if you guys want to check that out, because obviously I love Veritasium's videos, especially when he talks about like more of the math and the theoretical side of physics. It makes me feel as if like we're getting closer to our goal of actually understanding how the universe works mathematically. Alright, maybe we can raid someone. Let's see if we can raid someone. Cybuzz is streaming. Why don't we give them a raid? Okay, guys. We will commence to raid in Cybuzz's channel, so I will give you the raid command. You can copy and paste that if you like. So you can copy and paste that. I'm just trying to do it for myself. It's kind of hard sometimes. Okay. And we will commence to raid into Cybuzz's channel. Alright. I shall commence the raid right now. And always remember, guys, everyone is precious. You guys are just as precious as everyone else. And I will see you guys on Cybuzz's channel. So take care, guys. Bye-bye. And also, if you're on YouTube, comment below and hit a like and subscribe to the channel if you can. So take care, guys. Bye-bye.